Share screen. All right. Yeah, so we'll just hop right into it. I'm gonna try and go as fast as I can, but kind of have a lot to cover. So I'll start with just opening up where the flight code is located. So if we're in the main MSAT page of GitLab, we'll go to NS8, and then Mr. CDH is the flight code.
Can you kind of give us a high-level overview for the dummies out here of what the goal is?
So what I'll be covering today is the flight code for Mr. Sat. Mrs. Sat is separate. I won't be covering that today. And for Mr. Sat, we have, what I'll be covering is what is on the main Raspberry Pi, which we call our flight computer. We have a secondary Raspberry Pi that communicates with this code, and I'll kind of touch on that during this training. And that controls the SI cameras and the SI algorithm and does everything with the stereoscopic imaging. And then there's a couple things in here, but that I'll discuss later, but there's also microcontrollers that communicate with the Raspberry Pi. That's where we have code stored in here for the microcontrollers, but that's also separate.
This is 100% C++?
Yes, yeah. With the exception of the microcontrollers, that's written in C. But I'll cover the microcontroller stuff towards the end of this. Does that make sense for everyone? Any immediate questions? I will probably talk fast. I'll try my best to talk slow, but if I'm talking too fast or if there's a question, just go ahead and interrupt me. You don't gotta wait for like a sweet spot. I tend to talk fast when I present. So if I'm going too fast, someone just yell at me real quick. But yeah, otherwise we'll jump right into it. So by the end of this, I'll kind of cover how everything is organized. But right now we're just going to jump right into the source folder. So the source folder is where all of the code for the Raspberry Pi is located. The other subfolders back here go into other things. So if you're wanting to work on the code that's on the flight Raspberry Pi, source is where it's located. And then we have a handful of interfaces, but where the flight code is flight main. So there's our flight code right there. It's about, what, 26 lines of code? So pretty short, right? Not really. This will end up expanding into a couple thousand lines of code, if not closer to like 10,000 lines of code. But we'll start simple and then add complexity. So what we're looking at here is two classes, two structs, and a config file. Right, so these two right here are structs that we use to store our state data and debug data, which just holds information on any issues that might arise during the flight code. And then the config file is short for our configuration file. So that is how we set up the flight code before we actually run it. So here we can set parameters on if we want to start in a specific mission mode, which can be useful for a day in the life if we just want to test downlinking or some other test. We can also tell it to read data from the sensors, so act like it's the flight code, or what we call day in the life. The day in the life test, we give the flight code fake sensor data that we will read in as like a CSV or TXT file. In that read config file, so the state data and debug data, there's options in there to say, hey, read in data from files instead of actually talking to the sensors. So that's just one example of the configurations we can set. There's a long list that I won't really get into today. So just to kind of sum that up, we have two structs that we use to set the parameters for the mission. And then the read config file is how we kind of get everything located in one location. And then we have state. State is a class that holds state information that will be used by the state machine. The state machine is another class. So at the highest level of the flight code, we have two classes that kind of drip down into a whole bunch of other things. The state machine, which I will be the first one we kind of cover, is what actually controls the mission flow. That controls what mode we're in. It controls talking to all the sensors, all the microcontrollers, talking to Missisat. That controls everything. The state, it supports the state machine by just holding in data on the current state of sensors. That'll be the second thing I touch on, but it has a lot of booleans on like true or false on if the analog is alive, if the digital is alive and working, things like that. So up to this point, that's just setting everything up. And then flight code start is where it actually starts the mission, and the state machine controls things from there. And once this state machine, so the flight code is done, it'll end up pretty much deleting itself. We go into the state, we clean everything up in the state, and then update the config file on the last, update the config file on data, because the state data will get continuously updated by the state machine through the mission. So this update config file just cleans up a couple things at the very end. All right, so we'll pop back out. So we're going to go to state machine. So this folder state machine holds everything that I was kind of talking about, plus child processes that the state machine uses. So we'll start with the state machine. Let's see. So like I said, this is just simply a class, but it gets pretty tricky fast. These threads I will touch on here very soon, but you can see here we have functions that are each mission mode. So initialize, detumble, checkout, separation. Functions for all the mission modes. When we want to process commands that we get from the ground station, and so on. So like I said, the state machine controls the flow and communication between everything. So the state machine.
A really dumb question.
Yeah.
What's the difference between a thread and a function?
Yeah, so a function, I will actually wait on that because I'm going to touch on threads here soon.
Okay.
And then a whole bunch of functions to turn things on and off and so forth. And then the state machine, I mean, it's what? Yeah, almost 1,000 lines. So I'm not going to go line by line here. But at the highest level, all the state machine is a switch statement. So if you recall in the flight main CPP file where I showed like what the flight code is, we called start. This is what start is, and this is pretty much what the mission does, right? It's a switch statement that just, so I guess I'll back up. A switch statement, it's like if everyone knows what an if-else statement is. So a switch statement is a way to do that without having a whole bunch of if-else's. If-else's, a whole long line of that. You just have a switch statement, which means based on what the mode is, based on what the mode is, it will, like this would be 1, 2, 3, 4, 5. Based on what that switch statement is, it will do your kind of if else. That makes sense. That's probably a really bad explanation, but yeah. Yeah, so that's kind of a brief overview of what the state machine is. And there's actually one thing I did skip on the state machine. I think it's in the CPP file. No, HPP. Yeah. So I guess here I will start talking. I'll explain what a thread is. Yes, Ian.
Can you make the text just a little bit bigger?
Yeah.
Thank you.
All right, so a thread, so in programming, everyone's familiar with like an int name, right? Or MATLAB. It starts at the top and then runs through it line by line, right? So what a thread does, you can think about it as splitting off into two and running things pretty much simultaneously. What's really going on is you have the code that splits into two, and then the processor just bounces back between them really fast. And computers are pretty fast, so it happens almost simultaneously. So what each of these threads are, the threads are separate functions, you can almost think of them as, that runs at the same time as the station. So we have 7 threads.
So the difference of a function, and a function just runs till it's done and then goes back.
Yeah, yeah. So a function, right, runs in a line, where threads, you can have multiple threads that all run at the same time. A thread can run, you can have 6 threads that run the same function, but that means you have 6 functions running at the same time. Does that make sense? So we have 7 threads. The first 6 right here is all communication threads. So we have a thread for comm, talking to our radio, UART thread that talks to the IMU, our I2C1 thread, which will be changing to be a UART thread. Sorry, let me back up. Comm thread talks to the radio. The UART thread, how it's wrote right now, talks to it talks to the SI pi, that secondary pi I was talking about, but that's changing to Ethernet. So that UART thread will become an Ethernet thread. The I2C1 thread is I2C, I2C is a communication protocol that is talking to the GPS, but that will be changing to UART also, so that the I2C1 thread will change to the UART thread. One wire is how we use is what we do to talk to our thermal sensors. So that's a thermal sensor thread. SPI is for the IMU, and then our I2C0 thread, I2C0 thread, is for our digital board, analog board, and our sun sensors. So that one handles communication to multiple devices. So that's what these threads are. And then we have a thread for the data manager that handles communication to our GNC executable. So on what I'm talking about right now is all the code, one executable for the flight Pi. We have a secondary executable on the flight Pi that runs the GNC code. So you can think of it as 2 separate programs running at the same time. And we talk to them using a C socket, which I'll briefly cover later. But this is a thread that handles communication to that secondary executable. Any questions there on threads? Yes.
How can you be sure that one thread won't, because some of these functions will have to wait. Like if you ask for data from the SIPI, it will have to wait. So how can you ensure that that thread won't be just like taking, well, again, because the other thread will have to. I know what you're asking. Yeah. I'm right about to cover it. Okay, good. So yeah, that moves us into the thread buffers. So yeah, I'll go ahead and get the notepad out. So everyone can see that's fine still? Okay. So we'll start with what a thread buffer is, and I'll go into having a vector of thread buffers. So I'll name it TB. The thread buffer holds communication that the thread buffer holds the data that the thread got from the sensor. So, and it's held in the queue. So everyone knows what an array is, but it's pretty much a vector, right? So you have one long line of elements of whatever it's ints, strings, whatever. So what a queue is the same thing, but it's a special type of array where it's first in, first out, right? If you're in the queue, you're in the line, whoever's there first goes out first. So it allows us, it's a controlled way to hold data in a vector or an array without just being able to pull data from the middle or from wherever. So we can only pull data from the front. So at the highest level, the thread buffers
are just made of a queue. That's just, I'm going to say type B right now. Where type B can be anything. Like I said, it can be an int. It can be however we are storing the data. So then what happens during the mission is the state machine has access to these thread buffers, which just holds a long line of the data. So what it does, it pulls the most recent data and then gives it to GNC, and it just does that over and over. So if we come here to the vector, so we have a thread buffer for each thread, right? So we're going to end up having a vector of 7 thread buffers. So if we think of this as a vector, I'll just do TB1, TB2, TB3, and so on, right? Where TBs are thread buffers. So then TB1, we'll say, is for the GPS. So we'll have GPS 1, GPS 2, and so on, where that's just each data point. So each position point that GPS gets. And then same with TB2, we'll say that's the IMU, IMU1, IMU2, and so on. So we pretty much have a vector of thread buffers that just store all the data that the thread buffers have access, that the threads have access to 24/7. So as soon as it gets new data, it pushes that data to the thread buffer. And then the state machine also always has access to that thread buffer and just pulls data whenever new data gets in. Does that make sense? Okay. All right, let's move to state. So like I said, the state class, so not state machine, the state class, supports the state machine by just storing data. So if we look at this, we have a couple enums that we use, a really big namespace, but then here's the state. Right, so I won't go through everything, but you can see it's just holding a lot of bools on, if the battery's low, if we've separated from this is that, a whole bunch of things on just the current state of the satellite. And then based on this, the state machine knows how to act and move forward based on the information from the state. Make sense? And then we have the config files, which I won't go into a whole bunch again, but you remember that debug data we saw, right? That's just a struct. So this is just defines how these configuration files are set up. And I'm sure you remember seeing the update config file function that we use in the flight code. So all that config stuff just happens here. All right, moving into the data manager.
Okay, I have a question.
Yes.
So the config file, is that the spoofed sensor data for a day in the life?
No, that sets the parameters that tells the state machine to use that data.
To use the data or not? Okay.
Yeah.
So why?
And a whole bunch of other things. Do you have another question?
Yeah, but I'll think about it.
Just ask it real quick.
Well, why are there? So what was the type of debug data?
It's a struct.
It's a struct. Yeah. Like what was the struct called?
A lot. It holds a whole bunch of pretty much options for the flight code to enable or disable certain modes.
But it's for the state machine.
Correct.
So when the state information update, the state class, there are many variants. Right? When it's updated?
Oh, when is it updated?
Yeah.
Whenever something happens. So so you kind of think of it, the state machine uses state to store stuff. So it's like the state machine's memory almost.
The reason we do that is just to kind of break things up. Otherwise, I mean, the state machine's already 1,000 lines. So it's just a matter of making it a little simpler in its already complex environment. So like as soon as mississat is separated, the state machine tells think of it like this: the state machine tells the state that, so then the state updates that parameter, that variable, and then when the state is moving modes, it checks that this has separated, and if that is true, then it can move forward in the next mission mode.
Before I forget to ask this, is there any danger in having the flight code also do day in the life, use fake data, and that when we go and do real AIT, that code, when it runs, could somehow not be running in the proper mode?
You mean if like we don't set the parameters right?
Yeah,
Doing
something
that?
like, yes.
I mean, yeah, that's always an issue, but
Like
so,
almost like a
so
like a remove before flight.
yeah, so by default, the config file sets up for the flight code. So the only way for that to happen is if we manually told the flight code, or if we manually changed that config file, which would be pretty obvious in that 26 lines of code. Yeah, so like if we come back over here, this flight main, so we read the config file, like these are zeros, right? So by default, the config file sets it up for the flight code, like to run in space. And so what we are going to do for day in the life is initialize these and then change these two before we read into the config file. To tell it, hey, this is day in the life, this is the parameters we want to set, blah, blah, blah. All right, any more questions? Good questions. All right, so moving into the data manager. So like I said, the data manager, it actually spawns the GMC algorithm using a fork, which for simplicity right now, we can treat a fork the same as a thread. We can picture it the same. They're not. Threads are, how do I go about this? So threads take less resources to spawn, and threads can directly overwrite each other and communicate with each other using just like a made-up class called thread buffer. Where a fork, it's more resource intensive on the OS system to spawn it and operate it. But at the end of the day, it's just two. It kind of breaks off into two and then does things simultaneously. But to send data back and forth, we have to use a C socket, and that's just a special kind of protocol to communicate between two devices. Or in this case, our two devices are two separate executables. So that's what is going on here. So if we go to the HPP, and here we go. Yeah, so start data manager, right? It's the data manager itself is a thread, and in that thread we can spawn GNC, kill GNC, and because this is talking to GNC, the GNC algorithm, the data we get back from GNC will be the control data to control the satellite. So that's why there's a send thruster command and send torque command. Is what we get from GNC is GNC telling us how to fire the thrusters or torque coils to go where GNC wants us to go. So that's a high overview of the data manager. So now moving into the threads. So if we go back to state machine threads, I kind of already covered these pretty well. So yeah, so like I said, these are all the communication threads. Again, so one wire is for thermal sensors, I2C0 is for the GPS that's going to be changing to UART. I2C1 is for the analog, digital, and sun sensor boards. The SPI is for the IMU, and then UART is for the SIPI that will be changing to Ethernet. Yes.
How can we handle the data? I think I3C1 have a lot of data, not just one. How can we handle the data with one queue?
That's a good question that I don't know off the top of my head. But we might be able to look at it real quick. Right, so again, here we have the thread buffers, which are pointers, meaning that the thread buffers aren't actually stored here, right? They're stored on the state machine, but this thread buffer, or sorry, this thread has access to that memory to overwrite that memory, which will then tell the state machine, hey, well, or not tell the state machine, it'll keep the state machine updated on the data that we're getting from the sensors. Right, so we have start thread, and then so can you repeat your question?
The I3C have like handled not one sensor or data, some like analog board and digital board and so on. So
Okay, yeah.
yeah.
So that's I'm glad you asked that, because that made me realize I misspoke earlier. So the thread buffer is made up of sensor data, which I will cover here very soon. So this thread buffer will actually have sensor data, which will be made of multiple thread buffers, if that makes sense. How do I explain this better? So earlier I said there's one thread buffer for each thread. I misspoke. There's one thread buffer for each type of sensor data, which is why it's made up of sensor data. So the IMU will have its own, not the digital board. The digital board actually doesn't have any sensors, but the analog board has the magnetometer. So there'll be a specific thread buffer for the magnetometer. And then the analog board also has the pressure transducers. So there will be a specific thread buffer for the pressure transducers. So yeah, I misspoke earlier. But yeah, so I mean, since we have this open, I can kind of just show you what's going on, right? So the thread buffer, or the thread's purpose, is to get data from the devices or sensors, and then give that to, or update the state machine, right? So you can see the functions here. Read the magnetometer, read the sun sensor, read the pressure, ping those devices to make sure they're still alive, things like that. So each thread has functions like this, where it can ping the boards to make sure they're alive. It can get data from the sensors of boards. In this case, because it's an I2C thread, we have process and read I2C functions. All right, so moving on, we're going to go to hardware interfaces. So all the threads have functions they use to talk to those devices. All of those functions are in hardware interfaces in here. So if I go back to, if I go back to one of the thread buffers, one wire, you can see one that includes takes us to the hardware interfaces and takes us to the files there. And yeah, like I said, for the sake of time, I'm not going to touch on every single one, but all of these are devices the flight Raspberry Pi has to talk to. So then in each of these folders, there's functions and code to pretty much handle that communication. And the reason we have it separate is so that here, where you see analog interface, digital interface, so on, these are files that we can compile and turn into executables and run separate from the flight code to test the communication between all these devices. So these is actually what we use for command execution testing, meaning it's just testing all the possible commands the Pi can send out. And in these interfaces, we verify what we get back and make sure that connection is good. So the nice thing about this is that this is verifying a decent amount of the flight code without actually having to run the flight code. So it simplifies things a lot when we want to do unit level testing. And then, so the SI manager, and I guess for organization purposes, we're still in source. So in source, we have the interfaces, the flight code, the hardware interfaces, which I just covered, the state machine, which I've covered. Let me go in the right branch. This test interfaces is no longer there. And then we have the SI manager. The SI manager actually isn't used by the flight Pi. It's stored here to test compatibility with the code we write, but the SI manager is actually used on the SI Pi. So our secondary Pi has what we call a Git module / dependency to this repo and specifically to this folder. All that means is in the other repo or repository for the SI code, there's a link that takes us to this repo so that the SI code can call the functions and the code we wrote in here. Does that make sense? Okay. So I'm not going to cover that, but that's what SI manager is. So moving into communication, this guy is a little long. There's a lot of stuff in here. And I'll try and go through this fast. But you remember seeing sensor data for all the thread buffers? So sensor data is the parent class for all the other types. So if you look here, right, we have a class, and these are all classes. So I guess I'll just pop this up real quick and then pop up an example. All right, so sensor data is just a class with a whole bunch of things. And it's a partially filled class that you can't really do anything with. And the reason, so I guess let me back up. Sensor data is the parent class of all the other sensor data classes. And what I mean by that is, for example, the magnetometer has a specific class for that data that's made from the sensor data class. The reason we do this is so that we can add a vector. So in the thread buffers, we can have a generic type of class because a vector has to be made of all the same thing, right? So we can't make a vector of a thread buffer that has different sensor types in it. So we make what we call the sensor data parent class, and then we cast each of the specific sensor data classes. So mag data will be casted as a sensor data and put into that vector of thread buffers. Does that make sense? That's kind of a lot of words there. A little confusing, but this is my software people understand that.
Yes, but I kind of forgot how inheritance works
Yeah.
properly, because if you cast it to a more general type, then put it in the vector.
Yeah.
And then you try to access those elements as, let's say, like you try to access CDMag.
Mm-hmm.
You know, it's of type sensor data. Sensor data doesn't have CMag, only mag data.
Correct, but so the way around that is to call the public functions, which then the functions are the way around that, right? Because in here the data is private. So using format data, it can take the specific class
and grab the data from that specific class.
Okay. I don't get it yet, but.
Okay. But, so that's the general idea. So I'm not going to go through each one, but you know we have IMU data, MAC data, SI data, and so on. And there's a handful of other things in here I want to touch really quick. So COM data is just a class to handle our downlinking. So communication data, COM data. Yeah, for time's sake, I won't go into that today. Command data is used by the state machine to send commands to all the threads. So really quick, if we come back here to the state machine, we also have a thread buffer of command data. So there's actually two thread buffers, or two ways we use thread buffers. One, to store sensor data. The other, to store commands that the thread buffers will, that the threads will continuously read from the command data buffer to see if it's received the command. And then we have engineering data, which is a type of data that we define, which is just a collection of our sensor data that the COM data uses. GNC data is really just a namespace that organizes how we send data to the GNC algorithm. So in here, it's just a whole bunch of constants, but it pretty much defines the vector or an array that we send to GNC, because we just send them one long array of data. So this kind of formalizes or standardizes how we send that array. So in here, yeah, now we have sensor data types. So GPS data, IMU data, MAC data, SI data, sensor data. So the socket is just a class that facilitates communication between the flight code and the GNC executable, like I've kind of already talked about. Sun data, thermal data. You have the thread buffer, which is actually defined here. I won't go into it, but this is where the thread buffer is defined. You have the UART connection that facilitates communication over UART. Commands is just a long namespace or multiple namespaces of all the commands we can possibly send to any of the devices from the Raspberry Pi. Then we have logger. So I was going to touch on this a little bit more, but I don't think I will be able to. So during the mission, we have log files, which by the name you can probably tell what they are. So the state machine, anytime something happens in the state machine, that it's logged into the log files. So at the end, we can downlink the log files, and we just have a long list of actions the state machine has took. So real quick, I can just show you an example. State machine, being the CPP. Yeah, I mean right here. So state machine log. So as soon as the state machine opens up, the first thing it does is logs that it's been created, and then state machine started, initializing COM, things like that. Just so that at the end of the mission, when we downlink everything, we can see how the state machine, or we can see the flow of the state machine during the mission, and we can identify what went wrong where, if anything went wrong.
Is it just one big file, one big log file?
There's multiple log files. So there's one for the state machine. I think there's one for each thread. Yeah, there's one for each thread. So the state machine is its own thread. And then like we have the data manager thread. Each communication thread has a log file.
Those files don't come down until downlink mode?
Yeah, correct.
So if something horrific happens mid-mission, then we don't get those.
Well,
Like on a local pass.
yeah, so I don't think it's implemented right now, but we plan on implementing if we have to restart, we just move straight into downlinking. It's like if the batteries get too low and the Pi just turns off, and the solar panels charging the batteries happens like automatically. We don't turn that on and off; it just happens. So if the batteries were to just die for whatever reason, as soon as we come back around in the sun, it just automatically starts charging. We'll reboot the Pi and then immediately move into downlinking. Once we have charged the batteries enough, move into downlinking and downlink everything. So those log files are continuously saved after each log, so that if we're mid-mission and something does happen, those log files are saved. All right. Let's see, where was I? So yeah, that's what the log files are. Packet. So a packet is a message, but it's just what we call in the software world a packet, or electrical communication world. So the packet just standardizes how we want to structure our messages, and that's used by the socket and the UART classes. So nothing fancy going on there. And then we have picture. We have two functions for pictures. Got my notes somewhere. We'll just pop it up. It pretty much just handles how we do stuff with the pictures that the SI algorithm will send to the flat Pi. So we can search and send. We can search for a specific picture and send it to something over the UART socket, or we can take a whole folder or directory and then send that. So this is actually used by the SI algorithm also. All right, so that covers the Raspberry Pi flight code. I'm going to touch up on the rest of the organization of the repo, but this kind of concludes the flight code for the Raspberry Pi. So are there any questions?
How long has this repo been in development?
I'm not sure, because before we had everything in different repos. Each thread had its own repo, and then at one point they were all combined into one repo. So when it was combined into one repo was 2 years ago. But I don't know off the top of my head before then when each repo started. All right, so yeah, everything I covered, all that mess of code and whatnot, was in source. So what's happening outside of source? So CMake is just a fancy way we can compile all that code with one command. And I'm sure throughout me going through source, you saw CMake stuff everywhere. Like every folder will have a CMake. All those link together to this top CMake that tells the code, that pretty much links everything together so that we're not missing anything. And that includes linking any libraries that we use. So if we learned this recently the hard way. If there's a new library we want to use, we have to make sure it's in the CMake, otherwise the flight code won't recognize it. Even if we have like include statement at the top, a lot of times that doesn't link it properly just because of the way CMake is set up. And then we have deps. So this is deps and the Git module are related. So actually, if you go to the Git module, it'll tell you to go to deps and then go to this link, which will be located in deps. So deps is short for dependencies. And like I said earlier with the SI algorithm,
that is dependent on the Mr. CDH repo. This repo is also dependent on the MSAT library. What's dependent is the wiring pi libraries, which is why here in the README, in the setup, we have git submodule update, and we make sure we have the right version of wiring pi set up. And then I think also, at least at one point, some of the log files were dependent on the MSAT library. I don't think that's the case anymore, but I might be wrong about that. Any questions on there? Okay. So then MCU. So MCU is microcontroller. So this is where all the code is for it. It's not as extensive as the flight code because the microcontrollers aren't doing nearly as much. They just read data, send data to the Raspberry Pi, or control the thrusters, isolation valves, and or torque coils. So they pretty much update the commander and receive commands from the commander relationship with the Pi. So we have the analog and digital board. The GPS, we used to have a microcontroller to talk to the GPS. That's no longer the case. So this is kind of old code sitting in there. But it's because that code has been verified to work with the GPS, and we're reworking the Raspberry Pi communication to the GPS. We're keeping this here for now for a reference. But that's what GPS is, and that's not used anymore. And then source, and then we have Clang format. Clang format is, I'm not super familiar with it, but I know it's a way to like organize, or not organize, a way to method your code. So here in the format.sh, that will call the Clang format. The Clang format is just a long list of settings, pretty much, that will standardize indentations. This for some OS systems, the indent is 3 spaces, others is 4. It will also automatically delete any white space. Like if you have white space at the end of a file, it'll delete all that and just have one white space with a new line character at the end. It does a whole bunch of formatting things that I'm not 100% familiar with. And then, yeah, you have the README, and that kind of sums it up. So there's probably a lot there. Sure, it went over most of your heads. But are there any questions? It can be specific or general.
How would you say we're doing schedule-wise on like code development?
Actually, in the past like 2 weeks, we've actually made like most of our progress compared to the rest of the semester. So pretty good. We're kind of doing the easy part right now, which is setting up all the hardware interfaces. Like Miles working on the TCP connection. Jonathan's working on the GPS connection. They're making good progress with that. But it seems hard, but that's the conceptually easy part. The conceptually hard part is implementing those changes into everything I just talked about. Right, because those threads are dependent on those hardware functions. So when we update those hardware functions, we have to update the threads. But when we update the threads, we have to make sure it's the threads. Well, we have to make sure the state machine is up to date with what the threads are capable of doing. Yeah, I won't get into it, but like the state machine will initialize each thread and then send commands to the threads to do so. But if we've changed the functions, some functions that correspond with a command might be obsolete, or you might have to, yeah, there's a lot of intertangling between all these classes. So that, I wouldn't say hardware-wise, it's easy, because there's no hardware, but that's where it gets conceptually hard on the software side. Because you can get the code to compile, but that doesn't mean it does what you want. And if everything is software, then like the only way to test it is to run the flight code, but the flight code will run for a while and it's hard to catch things, and yeah, it can be a complicated process. Okay. Anything else? All right, cool. Let's see. Who wants to do the chant? Do you have any volunteers? No? There we go.
Why not?
All right.
Okay. 1, 2, 3.
Set.
Is it 1, 2, 3? Is it 3 to 1?